Hi, my name is Nic Bester. I'm a structural engineer for Oricon in Cape Town. The building is separated into two main components. The one on the inside is the internal frame, and that comprises of a reinforced concrete slabs and reinforced concrete columns. Draped over that and separate from that is a continuous 220 mm thick reinforced concrete shell. The shell is supported on eccentric steel column connections, so it's raised approximately 2 meters above the ground to make it appear floating. Given the nature of that support, the walls actually want to fall out, and so there are steel ties that tie the wall back and actually hold the wall and balance it from falling outwards, and those tie back to the slabs. On the western external facade, there are reinforced concrete stairs that are hanging off the building and are supported by tension rods, which as a prop cantilever, and the tension rods extend through the facade and tie back to the slabs. Inside the building, between the internal core and the concrete frame, there's about a 2.5 meter gap, and that at one portion is filled with a structural steel lift frame, which connects the two and also provides lateral stability to the building. And to provide access in the building, there are 3 sets of hanging steel stairs which hang from tension rods from the roof. On the eastern portion of the building, there is a courtyard space with a structural steel canopy. Inside there, on the ground floor, there's an auditorium which features a 16-meter column-free space, which was made possible using two double-story reinforced concrete or composite reinforced concrete hanging columns which hang from the apex of the frame. So given the very stringent aesthetic requirements of the project, it was very important that all the steel to concrete connections were very neat and were not bulky, which meant that they had to be relatively small and embedded. One of these connections, as I mentioned earlier, was and a very important connection for the structure, is the eccentric connection between the facade wall and the floating facade wall and the steel columns. This connection is it's an eccentric connection. In other words, the 220 mm thick facade wall sits eccentric from the steel columns on the inside, which helps the facade wall to look like it's floating off the ground, and you never actually see it because the steel columns are hidden behind a glass facade. So from the outside, it looks like the shell is floating. This connection was a very important connection from a structural point of view. Over and above all the design checks that we did back in the office, it was obviously very important that our proposed solution could actually be achieved on site. So in other words, it was constructible. And to do this, we had to sit down with a contractor and workshop a solution that would work. I think one of the well-known benefits of steel as a material is its efficiency in terms of its strength to weight ratio. For a very high load, you could have very slender or small member size, and I think that was fundamental to this project, to making the actual facade wall appear to be floating. I don't think there was any other structural material that would have been able to achieve the same slenderness of those columns, and therefore the floating nature of the facade. On a personal level, I'm most proud of being able to be part of a project team that was able to provide a library in the first university built post-94 in South Africa, and not just any library, but actually a landmark building that provides unmatched learning space and resources for students in the area.